Intermolecular forces. Alright, so let's talk. There's intermolecular forces and intramolecular forces. Alright, so there's a difference. It's just this little spelling. So intra. Alright. And so what's the difference? Alright, intermolecular forces are between molecules. Whereas intramolecular forces are in the same molecule. Right? So think of intra, think bonds and that type of thing. Intermolecular forces, these are a force between two or more different molecules or atoms. Right? So these are like one water molecule to another water molecule, one nitrogen atom or nitrogen molecule to another nitrogen molecule, a gold atom to something else. All right, it's not a bond though. Okay, these hold molecules together in the solid and liquid states. Alright? So they hold the molecules together in the solid liquid states. Alright? Because, I mean, if you ever thought about it, you've probably done the valence electron count and the VSEPR theory Lewis structure of water. Well, water, can't violate the octet rule, but yet ice forms. So how are those water molecules bonded to another water molecule, or how are they stuck to another water molecule to make ice if there's no more bonds being made and nobody's violating, oxygen and hydrogen are not violating the duets or octet rules? Right? That's a good question. Okay? So these intermolecular forces are what hold like ice together, or dry ice, carbon dioxide together, and that type of stuff. These are electrostatic in origin. Let's spell it right. Right? Which means it's due to the electrons. Right? And a lot of times we call them van der Waals 2A's forces. Alright, so there's really 4 of them. There's one with ion dipole. Alright, so ion dipole. It's the first one. These occur between ions and polar solvents. Alright, so this is really important for sodium chloride, table salt in water. Right? It's, when you talk about table salt, it dissolves in water to a certain point. Why does it dissolve? Well, right, it doesn't decide, right? There's actual reasons for it dissolving, right? And there's the ions, Na plus, Cl minus, and water. They have an interaction, and it's a very strong interaction. Alright, so it's favorable for some salts to do this. And so when we say strong, it's 10 to 50 kilojoules per mole. Alright? And of course it's important for aqueous solutions with ionic compounds. So the first one, ion dipole. That's the strongest on average. All right. Okay, and what does it kind of look like? Well, take sodium chloride for example. If I have Cl minus or Na plus. Not to scale, because chloride is way bigger than sodium. But what's going to happen is water, we know that if chlorine's negative, the positive side of the water will be around the chlorine, right? And it's going to look somewhat octahedral, these small ions. And so a lot of times we'll write H2O, OH2 to show that, right, what we have going on is hydrogen is going towards the chloride. Conversely, with sodium, right, we're not going to have hydrogen. We're going to have oxygen nearby, right? So we write it as H2O and OH2 that way. So it shows you the oxygen is the closest, if that makes sense. So we know we write water H2O, H comes for O, right? But when we write it like it is down here, we write it OH2 because of this. Now, that shows you that ordering, that interaction, these interactions here are those ion dipole interactions, right? And it's a relatively strong interaction. Okay. The second force that we'll talk about is hydrogen bonding. Now, hydrogen bonding is not a bond. All right, it's not really a bond. It's a very, very strong force between molecules. All right, it's a very strong force. So now we have, all right, it occurs, all right, in polar molecules with H to F, HF, so HF, H to O, or H to N. Alright? Okay? Because when hydrogen bonds directly to F, O, or N, the bonding atoms such as fluorine or oxygen or nitrogen, including hydrogen, right? So HF is an example here, right? Acquire, so H and F, like if you look at HF for example, they acquire relatively large partial charges. All right, so it's not just like, I mean, not that, again, human behavior, nothing to do with chemical behavior, but if you were to go to Subway, let's say you eat there, and you were going to split a foot-long sub between two people. This is kind of like having one person get a bite of the sub, and then the other person get the whole other rest of the sub. Like, it's almost like you didn't get anything. All right? So giving rise to strong dipole attraction to neighboring molecules. So really, because the third intermolecular force we'll talk about is dipole-dipole. Hydrogen bonding is basically a super duper big dipole-dipole interaction. and it occurs with H bond to O to bond to N. So when we look at this, like look at, for example, NH3 is an example. H2O is also an example. All right, and so NH3, I got N, 3 H's, N, and 3 H's. All right, and if we look at the electrons here, what can happen is this hydrogen bond can form between that lone pair and this hydrogen, and it's an interaction between them. All right. Okay, and just let's put some examples out here for you guys, because I want to show you the difference between like what these properties are due. So this will be a foreshadowing here in a second. So water, if we look at water's hydrogen bonding, I have let's just say HOH, HOH, HOH. So if I draw water's Lewis structures here, right, with the 8 valence electrons, right, the hydrogen bond can be, this guy with this hydrogen, let's say, this guy with that hydrogen. All right, and so we can have these things. Now, if you look, water obviously has a melting point of 0 degrees Celsius and a boiling point of 100 degrees Celsius. Ammonia has a melting point of negative 77.7 degrees Celsius and a boiling point of 33.4 degrees Celsius. So put that in perspective. If we throw in CH4 here, which does not have hydrogen bonding, the melting point of CH4, I believe, is around negative 182.5. And the boiling point of methane, I believe, is negative 162. Alright, and so one of the things we're going to get to is that the stronger the intermolecular forces are, the more likely we're going to be a solid or a liquid. And the weaker the intermolecular forces are, the more likely the substance is going to be a gas. So if you look at this, you can deduce that hydrogen bonding in water is stronger than the hydrogen bonding in ammonia, because water has a much higher boiling point and melting point than ammonia. Right, and this is negative 33.4. All right, and why? Well, water can make 2 hydrogen bonds per 1 H2O molecule, because there's 2 lone pairs. Ammonia can make 1 H bond per 1 NH3 molecule. So it's a 1-to-1 ratio. And so the fact that there's 2 hydrogen bonds per water, this really strengthens the interactions of water and makes it way, like, because again, we'll get to there, methane does not weigh that much. Methane, ammonia, and water all weigh relatively around the same amount, right? Water weighs 18, ammonia weighs 17, methane weighs 16 grams per mole. So they're all relatively really close. Or it's just 2 grams per mole heavier. Not a big difference. But the boiling points are hugely different. The melting points are hugely different because such strong intermolecular forces in water. All right, and that's really important. And just so you know, that the distance here, if we look at the bond of water, is approximately 96 picometers. The hydrogen bond is approximately 300 picometers. So it's almost 3 times as large. All right. The second or the third, excuse me, the third interaction is dipole-dipole. Right? And this occurs between polar molecules. Right? And we're going to say it's moderate strength. I'm going to say it's moderate strength. Alright? Not super strength, but moderate strength. Okay? And so, like, for example, HCl would be a prime example. So if we draw all the HCl bonds, if you notice, right, the chlorides are going to be slightly negative, delta negative, hydrogen's delta positive, right? So they're almost like magnets. And if you notice, positive, negative, negative, positive, positive, negative, right? They can orient themselves kind of like magnets do, right? This interaction does matter. Okay? All right? And so it helps keep things solid, liquid, and whatnot. It's not as strong as the hydrogen bonding, but it can be pretty strong. Last one. Dispersion forces, or London dispersion forces. These occur in all atoms, all free atoms, and molecules. And what it is, it's an instantaneous dipole induced dipole. Alright? And so, again, human behavior is nothing like chemical behavior here. But imagine you're on a boat. You're on a small boat with a bunch of people driving next to another boat with a bunch of people. Alright? Where I live really close to the intercoastal waterways and ocean. And so people could be on the boat and somebody might say, hey, look at the dolphin. And everybody goes to one side of the boat to look at the dolphin, especially if they're littler people, right? Well, that'll cause the boat to turn temporarily. And if it turns towards the boat next to it, that might make a reaction from the boat next to you. Like, whoa, he's coming, what are you doing, right? Okay, same thing happens, it could be happening when you're driving. I mean, people text and drive all the time, unfortunately. Right? And if they're on, they start to swerve, it might cause the car next to, in the lane next to swerve, right? These are induced behaviors, right? You're reacting to something else. And so what happens here, and there's a picture here of helium that we'll get to that shows this very clearly, where you have the electrons on one side of the atom. So if I have two atoms of helium, right, there's two electrons floating around. So electron, well, that's on the same side, but they're both going around in a cloud, right? 3 dimensions, right? Well, if they both have a cloud, but let's say this helium has both of its electrons, let's use a different color on the left side, right? That means in this helium atom, it's going to be temporarily, for just a brief moment in time, right? We're talking probably, faster than like picoseconds, femtoseconds, attosecond time frame, maybe even faster than that, right? How there's going to be a slightly negative and a slightly positive, right, section for just a brief moment, right? And so this helium atom right here will induce a dipole on the purple one, right? So the pinkish one will induce a dipole on the purple one, right? Now, okay, these depend on what we call size and polarizability. All right, so size. Larger is stronger or more forces or interaction. Right, so bigger molecules have more dispersion forces, and more polarizable is more force as well. Well, what's more polarizable? Let's give you an example. If I have a big hydrocarbon, C, 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 then H is all around. Alright, so I have this hydrocarbon. Alright, and let's bond it. 2, 4, 6, 8. Right, and the chemical formula would be what? C1, 2, 3, 4, 5, C5, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Okay, now there's another way to draw C5, H12. If I draw it C, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We'll do this one in purple. Alright. So this one's more, it's a shorter molecule. It's more like that's carbon's tetrahedral, but it's more compacted, right? So if you notice, the longer one, this one is longer, and so it's more polarizable. Why? Because the electrons can be more pushed to one side or other. The electrons in can be shared, can be temporarily pushed to one side or the other. Where here it's not as long, so it doesn't work that way. All right, it's less polarizable. So these longer, straighter molecules are more polarizable than these more compact molecules. All right. So the first figure I'll show you here, and this is table 11.4 in the textbook. Right, dispersion, and here's an example of dispersion where you have the two electrons on one side influencing the two electrons on the other side, and it's 0.5 to 20 kilojoules per mole plus. Now, because again, it depends. If you look at dipole-dipole interactions, this occurs between polar molecules. You have, this would be COH2, right, formaldehyde, and that's interacting with another formaldehyde. Hydrogen bonding, molecules contain H bond to F or N. There you go. And then there's ion dipole. All right, and so there you go. There they are. There's your ion dipole forces. That's the picture we drew to begin with. There's your hydrogen bonding in water. There's your dipole-dipole interaction. So there you have acetone or interacting. And so when you look at this electrostatic potential map, some of these are in your textbook or you see them. This means, again, electron density. All right, what we say about electron density. All right, so if you were in my class for Chem 1, we talked about the hydrogen atom and how fast that electron's going around, how many times it goes around the atom in a second, and it's trillions. It's like everywhere. No matter where you touch, the atom, you're going to touch the electron. The electron's going to run into you. Right? It's almost like a solid. It's moving so fast. And so this is high electron density. and this would be low. Low electron density. Right? So think of it as, a good way to think of it as a mattress. All right? This is a very, very soft pillow top. You sink in and disappear, right? The mattress is still there, but it's very, very soft. Where this, the orange red, is like a hard mattress, firm mattress, where you push in and you can hardly push in. All right? And then this is in the middle. The green's in the middle, where you can push in a little bit. All right, and so that's a good way to look at. It's still there. There's still electron density there. It's just not very, not a lot more by the oxygen. And then here's your dipole, induced dipole. All right, so that would be an example of the intermolecular forces that we have. All right, I don't think I have any more figures. All right, and so, for example, if we go back here to our notes, something I want to bring up is that the molar mass really plays a point into this. All right, big time. So the stronger, like for example, the noble gases. Let's look at the noble gases. Helium, neon, argon, krypton, xenon. Molar mass 4. Right, 20.18. This is grams per mole. Right, we got 39.95, 83.80, and 131.3. All right, so you have all those. Then what? Okay. Then we have our boiling point in Kelvin. So the boiling point of helium is 4.2 Kelvin. You can only get to 0, so that's really low. And as we gain in mass, we go 27 Kelvin to 87 Kelvin to 120 Kelvin to 165. All right. Another example would be the halogens. Right, and as we look at, you have F2, Cl2, Br2, I2, right? You have gas, liquid, solid, right at 25 degrees Celsius. That's the state of matter. So as you can see, our intermolecular forces are strongest for I2. So intermolecular forces, right, increase. Right? Increase as we go down. Okay. Now, what intermolecular forces does F2, Cl2, Br2, or I2 have? Only dispersion. Only dispersion. Another example would be hydrocarbons. So if I had CH4, C2, H6, C3, H8, C4, H10, C5, H12, C6, H14. Right? We start, this is a gas, 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 gas. Then we start getting into liquid. Liquid. And eventually they become solids, right? And all we're doing is increasing the molar mass, right? So the only thing that's increasing here is molar mass. So molar mass. As the molar mass increases, my intermolecular forces increase with my dispersion forces. All right. So if I look at the periodic table, solid atoms typically have more intermolecular forces than liquid, than gas. All right. So that is intermolecular forces. Now with intermolecular forces, right, many properties depend upon the strength of the intermolecular attraction. Right? So many properties of these molecules depend on the types of forces they have, how strong are the forces, right? And so those would be melting point, boiling point, right? Delta HV, which is the heat of vaporization. Right? Viscosity, the resistance to flow, right? Surface tension, and vapor pressure. So those are some of the properties that depend upon the strength of the intermolecular forces in the molecules.